All right, ladies and gentlemen, class recording started. So, yesterday we started in on chapter 3 on acceleration and accelerated motion. So, we introduced the topic of acceleration yesterday. How do we define acceleration? How do we define acceleration? Go ahead, Luke.
The rate at which velocity changes.
The rate at which velocity changes. So we're talking about a changing velocity. And then towards the end of the period, we talked about that in order to calculate the acceleration, we need to know two things. What do we need to know in order to calculate the acceleration of an object? Not just the velocity, what has to happen in the velocity. It has to change, right? So we need to know the change in velocity, and we also need to know the time over which that change occurs. And your book sort of expands this formula out here, right? To know the change in the velocity, we need to know both the initial and final velocity, and so those two formulas are the same, just one more detail than the other. Okay? Good there. All right. Looking at some of the homework problems from last night, just to review some of the concepts that we introduced yesterday. Homework problems were on page 81, I believe. Oh, not 3, there it is. All right, on page 81, one of the homework problems you had last night was number 11. Can an object accelerate even if its speed is constant? And the answer to that question is yes. We said that acceleration can take 3 forms, right? Physically, 3 things are considered acceleration. What are the 3 things that are acceleration? Speeding up, slowing down, changing directions. So something can't have a constant speed and accelerate as long as it's doing what? Changing direction, right? Something going in a circle is constantly accelerating, right? Because it's constantly changing direction. Okay. Good there? All right. Number 16. Number 16 says the velocity of a ball is 1 meter per second at a given instant of time. Is it possible for the ball's acceleration to be negative 1 meter per second at this instant? And the answer to that question is yes. In order to calculate or determine the acceleration of an object, we need to know not the velocity, but the change in the velocity. Meaning that we need to know at least 2 velocities. If we go back to this, right? If we go back to this, let's say that the initial velocity, or the current velocity, is 1 meter per second. Does that necessarily mean that the final velocity will be 1 meter per second? No. So while acceleration depends on velocity, right? It's not just velocity, it's not just change in velocity, right? So even though a certain object has a certain velocity right now, it can have a different acceleration than that value because its velocity is changing at that point. Okay. Good there? All right, the last one that I wanted to look at was number 19. Just to review one of the calculations that we did. All right, so number 19. Challenge, everybody. Here we go. So, I don't know exactly how challenging this is, but all right. So it says an object has an average acceleration of positive 6.24 meters per second squared for 0.300 seconds. At the end of this time, the object's velocity is positive 9.31. What is the object's initial velocity? So, even though we may be able to do this a little bit quicker, right, just to go through the process. What is this question asking us for? the object's initial velocity? Information they give us to work with.
Final velocity.
They told us that at the end of this time, right, the object's velocity is positive 9.31 meters per second, right? If it's talking about what's going on at the end of that time, that's going to be the final velocity, right? What else? They told us that it occurs over a time of 0.300 seconds. Okay? And then, the other thing it told us, okay, it tells us that the average acceleration is positive 6.24 meters per second. So, we start off, like I said, you don't have to show me this every time we do a problem, right? That's how we define acceleration, right? Change in velocity over change in time. We said that we can make it a little bit more detailed by making it look like this. Now, it's a matter of just solving for the initial velocity. I don't really care how you do it, okay? You can plug in numbers and then manipulate the numbers how you want to, or you can manipulate the variables first and then plug the numbers in at the end. Either way. So here, we manipulate the equation, look like that. Then go like that. And then because the initial is negative here, we'll just make everything opposite. Right? Like that. And then the initial velocity ends up being 7.44. Is that what it is? 7.44. Kind of sad that I remember that from this morning, but just because I remembered it from 6 hours ago. My brain is filled with this useless information that's so. Okay. Good with the homework review stuff that we did yesterday. Okay. If you have your book, flip to page 76. In the bottom left-hand corner of page 76, there is a picture of a kid sledding down a hill. And in the top right-hand corner of page 77, there is a data table that gives you more information about that kid sledding down the hill. So what I would like you to do first is take 30 seconds and talk to the person next to you, or wherever, just on your own, and determine for me from this information, one that you have in your packet, one that I gave you and is in page 77 of your book, what is the acceleration of this kid as he is sledding down the hill? Discuss. Go. Okay, so what is the acceleration of this kid as it's sledding down the hill? Not good. 0.5 meters per second squared, right? So acceleration of this kid is equal to 0.5 meters per second squared. So let's talk about it, right? What is so okay, let's take a look at this number right here. We said that another way of looking at an acceleration, especially because of the unit that's on it, is 0.5 meters per second for every 1 second. Because the acceleration tells us what? What does acceleration tell us? Change in what? let's go with something a little more general. Change in the velocity, right? So acceleration tells us how much the velocity changes every second, right? And from the picture, you can kind of see for the 2 seconds, but also in the data table, it gives you a little bit more information, that every second that goes by, the velocity in this case increases by 0.5 meters per second. So we keep going 0.5 meters per second faster for every second that goes by.
Now, does it always steadily increase?
That's the point of this discussion right here, okay? So this, and it says, here it says in your guys' packet on page 3, also in the book on page 76, this acceleration that we're showing in this picture of the kid with the sled and in the data table on the next page is a constant acceleration, okay? So if I flip it up here, constant acceleration, hopefully in a kind of a duh moment, right? It says that the definition of constant acceleration is acceleration that is the same at every instant of time. So when something constantly accelerates, what happens? If something constantly accelerates, what happens? The velocity is constantly changing. Very well said, right? That the velocity is constantly changing. That means it could continuously get faster and faster and faster and faster, or it could continuously get slower and slower and slower and slower, or it could continuously change directions. Going in a circle is a constant acceleration because it keeps changing directions, okay? So Caitlin, in this case, and for pretty much every example that we're going to do in this class, we will assume that the acceleration is constant. In real life, that isn't always the case, but that gets more complex. So in this case, we're going to deal with constant acceleration motions that will continuously either get faster or slower, okay? Krista, go ahead.
Even though your speed isn't changing, the velocity
Right. Now, Krista, that's actually, because that's a constant acceleration, okay? Krista, that actually is a little bit more complex of a situation that we're not quite equipped to deal with yet. Chapter 8 on that. So. All right. Next, on page 77 and also on page 3 of your packet, you have this graph. So let me get this graph here so I can write on it. Bigger. Okay, so first, we talked about in the last chapter that it's perfectly fine to look at a set of data or a picture or whatever it is, and from this set of data, we determined that the acceleration was 0.5 meters per second squared. But sometimes we have more complex data or more data that we have to analyze, and making a picture out of that data sometimes makes the relationships easier to see. So, this is the graph that represents the data that was in the data table that we just looked at. Okay? So first, one big difference between this graph and the graphs that we were looking at in the last chapter. What's the big difference between this graph and the previous graphs? Okay. This is a velocity versus time graph. That's a terrible color. Not very Highlander-ish, if you ask me. This is a velocity versus time graph as opposed to a position versus time graph. Okay? So, what does this graph tell us? Eventually, yes. Let's go more with like a duh sort of answer. Like, what does this graph tell us? Duh. It tells us velocity and time, right? So it tells us what an object is doing, but what doesn't it tell us? It doesn't tell us where it is. This graph for the kid riding his sled down a hill could be exactly the same graph as a kid who is riding his bike down a hill, right? We don't know. This graph doesn't tell us where, it tells us what. Okay? So, in this case here, right, what is this graph telling us is happening to the velocity? It's constantly increasing. Whereas a straight line on the position graph means what? It's a constant motion or constant velocity. A straight line on the position graph is a constant velocity. A straight line on this graph is a velocity that keeps increasing, right? As you can see down here, right, the slope of this graph also tells us something else about this motion that maybe isn't as obvious as the graph information itself. Here, before we plug any numbers in, let's do this. We know that slope is rise over run, fine, okay? On this graph, using only the units, what unit are we measuring on the rise axis? Which unit?
Meters per second.
Meters per second, right? So we got meters per second here. What unit are we measuring on the run axis? Seconds. Hopefully this looks familiar. Yes, right? That's our unit for acceleration. So on this graph, the slope tells us the acceleration. Okay, then going back to the beginning part of this discussion, right? What do you know about the slope of a straight line? What has to be true about the slope of any straight line? It has to be constant, right? And so this is a constant acceleration because the velocity keeps continually increasing. Okay? Good there. All right. Down at the bottom of page 3 of your packets, which is also the bottom of page 77, is conceptual example 3.3. Do. I'm going to go here and go there. There we go. Sorry, everybody. Whoa, wrong one. Here, there we go. That'll look good on the video right there. That's professional right there. All right. So conceptual example 3.3, comparing accelerations. It says, shown at the right are velocity time graphs for two different cars, A and B, that are accelerating. Is the acceleration of car A greater than, less than, or equal to the acceleration of car B? Let's get this question out of the way and get on to some more interesting things. First, which one has the greater acceleration? B. Why? The slope's greater, right? So, the acceleration of B is greater than the acceleration of A. Fine. Let's talk a little bit more about this graph. Maybe something that isn't in the book, alright? So, how do these two cars start? What can you tell me about car A at the start and car B at the start? Go ahead, Luke.
Car B starts at 0, the car A starts at 4.
Okay. And when you say at 4, what are you trying to tell me?
That's velocity. It's already moving.
Okay. Car A is already moving at the beginning of this graph. But car B is not moving because it starts at the origin, not location. The origin on this graph tells us that the velocity is what? 0. What happens to the distance between car A and car let's go with this. Let's say, even though this graph doesn't tell us, let's say they start at the same spot at the same time. Okay? What would we see happen with these two cars? Discuss. Go ahead. Same position. Let's say they start at the same position. Even though this graph doesn't tell us that, let's say it starts at the same position. All right, let's discuss together. You guys are too small of a group to discuss with each other, so we'll discuss as one big group. All right. What can you tell me about the velocity of A compared to the velocity of B? There's a couple things you can tell me. There's one I'm looking for in particular.
Car A is bigger.
Car A has a greater velocity than car B. When?
From the starting point.
From the starting point
To that.
all the way to the end. Car A's velocity is always greater than car B's velocity, right? So if you see something that is always traveling faster than something else, what's going to happen? What would you see about the distance between them? It would increase. Okay? Car A is separating itself from car B, even though car B has a greater acceleration. The actual velocity is slower than car A's velocity. What happens there? They reach the same velocity. Are they in the same spot? No, right? The intersection of these two graphs is not the same as the intersection of the position graphs, right? On the position graphs, when the two graphs cross, that means they're in the same spot at the same time. That's where they meet. That's not the case here. The only thing that happens there is that they have the same what? They have the same velocity. What happens past that point on this graph? What would we see happening past that intersection point on this graph, Brett? So what would B start doing now? Now B would start catching up to A, because now B has a greater velocity than A. Up until that point, A is separating itself from B. It would travel farther, 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 farther. B is still traveling forward, but it's not catching up. A is separating itself from B. But from the intersection point on, now B would start catching up to A. Okay? Does that make sense? So differences between this graph and the position graph that we talked about. Okay? Good there. All right. Next, let's look at page 4 of your packets. On page 4 of your packets, that corresponds to page 78 and 79 of your book. And I'm going to get this all together because I want it all together. All right. Here are several velocity time graphs representing the motion of the bicycles in the 4 different pictures that are shown here. At the top, it shows a guy riding his bicycle. Picture A says that his speed increases. And I think that if I had to ask most of you, you probably could get that graph right there, that graph right there represents the motion of the guy riding his bicycle in picture A. Yes? Because, first of all, which way is he traveling? Positive direction, okay? We know that because where do these lines all occur? Where do they show up on the graph? How do we know they're positive? Because they're above what? They're above the x-axis in this case, right? They're above 0. 0 on this graph, the x-axis on this graph, is not a location. The x-axis on this graph tells us what about the motion? What does the x-axis represent on this graph? Okay, time is being measured on the x-axis, but if this graph hits the x-axis, what does that tell us about the motion? Zero velocity. So if this graph hits the x-axis, that means that the object stops, right? All of this graph that I've highlighted in green is all above the x-axis, representing positive velocities, but what's happening to those positive velocities? What's happening to the y values of that portion of the graph? Yes, they're changing. Specifically how? No. During this section of the graph. If we had to write the ordered pairs, right, what would be happening to the y values of those ordered pairs?
They're increasing.
They're increasing. Means that the object is speeding up. Okay? Good there? What's happening in that section that I just highlighted pink? Slowing down. What's the same as the previous graph? There's something about those two motions that's the same. Slope isn't the same. What makes those two graphs similar? Which way is the bike going in both of them? Positive direction, right? In this case here, right, here in this picture, if this arrow is pointing towards the right and it's labeled as X, that's the positive direction, right? So in this case here, both of these graphs represent motion in the positive direction, but the top one's speeding up, the bottom one's slowing down, okay? The two pictures of the girl riding her bike on the bottom. Big difference between the guy riding his bike and the girl riding her bike is what? Which direction they're going, right? And we signify or we distinguish that change in direction how? How do we distinguish velocity one way versus velocity the other way? Well, positive, negative, right? In this case, that's what side of the x-axis we're on. So in these two graphs down here in the bottom right, now all of those velocities are where? Negative. They're underneath the x-axis, right? What's happening there? What's happening there? The speed is increasing. Do you understand that, Luke, or did you just read it off of the picture? You can be honest. It's okay. Okay, you read it off the picture. That's fine.
I think I also understood.
Okay, why is the speed increasing there?
Because the velocity is decreasing because it's going.
So the velocity is increasing.
The velocity is increasing in the negative direction.
Would that be decreasing?
No.
Decreasing. Up there, approaching zero.
Decreasing
The
would be
more negative it, like, I understand that
Going fast, just think it's going faster and faster there.
yeah, but isn't that what decreasing is?
No.
No.
A decreasing velocity means that it is having less displacement every time. The negative sign tells us nothing about how fast an object is going. It only tells us which way. Negative 10 is faster than negative 5. Negative 20 is faster than negative 10.
Yeah,
Those are increasing velocities. They're just increasing in the negative direction. Okay?
Okay.
And then that means here, right, applying that logic, what's happening there in section A? Okay. Physically, what's happening to the girl on her bike there? Slowing down. Okay? So, I creatively use colors to try and illustrate similarities and differences. In this case, basically similarities, right? What's happening in both of the green colored graphs? Say again? Increasing velocity, or physically, Krista, what would we see happening to those bicycle riders? They're going faster, they're speeding up, right? And I use which color? Green color. So now, right, the two pink ones are both doing what? They're both slowing down. There's red.
Purple does not mean stop.
Usually it's yellow. Yellow means slow down.
This is clearly purple. If this was a real class recording, I would stand with my shirt next to this purple line and we would compare purple to purple. All right? Clearly pink. Clearly pink.
Okay. Even if it's pink, pink doesn't mean stop.
No, but if I use this,
You may want to
you
pause.
can't see anything. You can't see the line anymore.
Yeah, what's wrong with yellow? Yeah.
Yellow means slow down. That's what they're doing. Should have used yellow.
All right then. Okay.
Okay.
The point to this being, other than my apparently questionable color choices and highlighters, right? So, yeah, I mean, so I thought I was being slick, but thanks. I appreciate that you at least that you see the value of the green line. So let's do the green line then. All right. So in the case of the green line, let's go with this green line. We established that the velocities are in which direction? Positive velocity. Acceleration. We said acceleration on this graph is the slope of that graph. What kind of acceleration does it have?
Positive.
Positive, because it's an upward sloping line. When we had positive velocity and positive acceleration, what happened to the guy on his bike? Did he go faster or slower?
Faster.
Faster. Okay? Let's take it down to this green line, down at the bottom. What do we know about the velocities there? What sign do those velocities have?
Negative.
They're negative. It's a downward sloping line. Therefore, what kind of a slope does it have? Negative, meaning that the acceleration in this case, negative. If we have negative velocity and negative acceleration, what happened to this girl on her bike? Physically, what did we say was happening to the girl on her bike here? She is speeding up, even though the acceleration is negative. Right? Again, the negative sign doesn't tell us whether something is getting faster or slower. It only tells us that in relation to what the velocity was to begin with. If we have a -5 velocity and the acceleration is -5, it goes from being -5 to -10. Physically, what's happened to the object? Sped up. She sped up in the other way. All right? But here, these velocities are positive, but which way is this line sloping? Negatively. Therefore, the acceleration is negative, and it slows down. Here, these velocities are negative, but which way is the line sloping? Up. But the upward slope of this line is taking it closer and closer and closer to what? Zero. So even though it has positive acceleration, because the velocity is negative, it slows down. So a key point at the end of this section, and I know it's a key point because it's being key, right? Speed increases when velocity and acceleration have the same sign. Speed decreases when velocity and acceleration have opposite signs. We can't just make a overall statement that positive acceleration equals speeding up and negative acceleration equals slowing down. It's dependent upon what the current velocity is. Okay? Good there. Tomorrow, we will explore these concepts in lab. You will make a velocity versus time graph. You will figure out acceleration. You will figure out whether it's speeding up, whether it's slowing down. All the things that we've talked about over the past 2 days. Okay. Don't forget your homework for tonight. A combination of conceptual and calculation questions at the end of chapter 3.